Hello there. Welcome to Single Area OSPF version 2 concepts. So imagine that it is time for your family to visit your grandparents. You pack your bags and load them into the car. But it takes a bit longer than you planned for, and now you are running late. So you pull out your map. Okay, so there are 3 different routes. So one route is no good because there is a lot of construction on the main road, and it is temporarily closed. So another route is very scenic, for instance, but it takes an additional hour to get to your destination. So the third route is not as pretty, but it includes a highway, which is much faster. So in fact, it is so much faster than you might actually be on time if you take it. So in networking, packets do not need to take the scenic route. So the fastest available route is always the best. So OSPF, or the open shortest path first, is designed to find the fastest available path for a packet from source to destination. So this module covers the basic concepts of a single area OSPF version 2. Alright, so let's get started. Okay, so for the module objectives, so the module title is Single Area OSPF Concepts. So the module objective is, at the end of this video lecture, you should be able to explain how a single area OSPF operates in both point-to-point and broadcast multi-access network. So subtopics includes the OSPF features and characteristics, the OSPF packets, and the OSPF operations. Alright, so let's start with the first section. Let's talk about the OSPF features and characteristics. So, introduction to OSPF. So this topic is a brief overview of the open shortest path first, or OSPF, which includes a single area and multi-area. So OSPF version 2 is used for IPv4 networks. OSPF version 3 is used for IPv6 network. So the primary focus of this entire module is single area OSPF version 2. So OSPF is a link state routing protocol that was developed as an alternative for the distance vector routing information protocol, or the RIP. So RIP was unacceptable routing protocol in the early days of networking and the internet. So however, the RIP reliance on hop count as the only metric for determining the best route quickly became problematic. So using the hop count does not scale well in a large networks with multiple paths of varying speeds. So OSPF has significant advantages over RIP, that it has offered faster convergence and scales to much larger network implementation. So OSPF is a link state routing protocol that uses the concept of areas. So a network administrator can divide the routing domain into distinct areas that help control routing update traffic. So a link state, or a link, is an interface on a router. So a link is also a network segment that connects two routers, or a stub network, such as the Ethernet LAN that is connected to a single router. So information about the state of the link is known as the link state. So all link state information includes the network prefix, the prefix length, and the cost. So this module covers the basic single area OSPF implementations and configurations. So what are the components of OSPF? So all routing protocols share similar components. They all use routing protocols messages to exchange route information. So the messages help build data structures. Okay. So, which are then processed using a routing algorithm. So basically, components of OSPF includes routing control messages, data structures, and algorithm. Now let's talk about the routing control messages. Okay, so routers running OSPF exchange messages to convey routing information using 5 types of packets. So these packets, as shown here in the figure, are as follows. So you've got the hello packets, okay, so database description packet, the link state request packets, the link state update packets, and the link state acknowledgement packets. Okay, now these packets are used to discover neighboring routers and also to exchange routing information to maintain accurate information about the network. So for the data structures, so OSPF messages are used to create and maintain 3 OSPF databases as follows. So you've got the adjacency database. This creates the neighbor table. Okay. So you also have the link state database or LSDB. This creates the topology table. And you've got the forwarding database. This creates the routing table. Now, this table here contains a list of neighboring routers to exchange routing information. The tables are kept and maintained in RAM. So in the following table, take a particular note of the command used to display each table. So basically, if you want to see the content of the neighbor table, so we can view it via using the command show IP OSPF neighbor. Okay. Now the topology table can be seen using the show IP OSPF database command. And of course, the routing table, which is also similar to static routing. We can see the routing table via the command show IP route. Okay. So basically, the difference between these tables are as follows. So when you say neighbor table, okay, so it lists down all the neighbor routers to which a router has established a bidirectional communication. Okay, so topology table lists information about all the routers in the network. So the database represents the network LSDB. So all routers within an area have an identical LSDB. All right. So the last table is a routing table. So these are the list of routes generated when an algorithm is run on the link state database. So OSPF uses the SPF or the shortest path algorithm, or also known as the Dijkstra's algorithm. So each router's routing table is unique and contains information on how and where to send packets to other routers. Okay, so next would be the algorithm. Okay, so as what I'm saying, OSPF uses the algorithms called Dijkstra's algorithm, or also known as the SPF, or the shortest path first. So the SPF algorithm is based on the cumulative cost to reach the destination. So the SPF algorithm creates an SPF tree by placing each router at the root of the tree and calculating the shortest path to each node. So the SPF tree is then used to calculate the best routes. So OSPF places the best routes into the forwarding database, which is used to make the routing table. All right. Now let's talk about the link state operations. So to maintain information, OSPF routers complete a generic link state routing process to reach a state of convergence. So when you say state of convergence, we're talking about the stability of the network. So the figure here, okay, shows a 5-router topology, each link between the router, which are labeled. Okay. Now, this includes, okay, so establishing a neighbor adjacencies, right? So the exchange of link state advertisements, build the link state database, execute the shortest path first, and choosing the best route. Okay? Now let's talk about the first one, so which is establish neighbor adjacencies. So OSPF enabled routers must recognize each other on the network before they can share information. So an OSPF enabled router sends hello packets out all OSPF enabled interfaces to determine, okay, if neighbors are present on those links. So if a neighbor is present, the OSPF enabled router attempts to establish neighbor adjacency with that neighbor. Okay, so each of the router here will send hello packets to each other. That is establishing a neighbor adjacency. So the next step is exchange link state advertisements. Okay, so the link state advertisements, or the LSAs, okay, so after the adjacencies are established, so routers then exchange link state advertisements, or LSAs. Okay, so LSAs contains the state and cost of each directly connected link. So routers flood their LSAs to adjacent neighbors. So adjacent neighbors receiving the LSAs immediately flood the LSA to other directly connected neighbors. So until all routers in the area have the LSAs. All right. So the third one would be building the link state database. Okay. So after the LSA are received, OSPF enabled routers build the topology table. All right. So, or the LSDB based on the received LSAs. So this database eventually holds all the information about the topology of the area. All right. So the next step would be router will execute the SPF, or the shortest path algorithm, or also known as the Dijkstra's algorithm. So routers then execute this SPF algorithm. Okay. So the gears in the figure for this step are used to indicate the execution of the SPF algorithm. So the SPF algorithm creates the SPF tree. And then we have now choosing the best route. Okay. So after the SPF tree is built from the previous step, the best path to each network are offered to the IP routing table. So the route will be inserted into the routing table unless there is a route source to the same network with a lower administrative distance. So such as static route. So, right? So if you still remember, static route has a value or an administrative distance of 1. Okay? So OSPF has an administrative distance of 110. Okay? So routing decisions are made based on the entries in the routing table. Okay? So numbers here, okay? So 2, 20, 25, 2, those are the costs to reach the destination. So for instance, if our destination is 10500/16, okay? So that would be reference to R1. So 10500, okay, so is located on R2. Okay, so it's the LAN of R2 here. Now, if that would be our destination from R1, then the shortest path, okay, so to get into that destination is via R2, and the cost is 22. So that would be the cost between R1 and R2. This figure is 20, and you've got from R2 going to the LAN, okay, you've got 2 there, so that means it's 22. All right. So next would be the single area and the multi-area OSPF. So to make an OSPF more efficient and scalable, OSPF supports hierarchical routing using areas. So an OSPF area is a group of routers that share the same link state information and their LSDBs. So OSPF can be implemented in one of two ways, are as follows. Okay, so you've got the single area OSPF, wherein all routers are in one area. So best practice is to use area 0. Okay, so as always, if you are not given any area on the topology, it is considered to be an area 0. Okay, if we are working on a single area, it's always an area 0. So the next one is a multi-area OSPF. So OSPF is implemented using multiple areas in a hierarchical fashion. So all areas must connect to the backbone, okay, so which is area 0. So routers interconnecting the areas are referred to as the area border routers, or the ABRs. Okay, so the focus of this module is on the single area OSPF version 2. Okay, so how about multi-area OSPF? So with multi-area OSPF, one large routing domain can be divided into smaller areas to support hierarchical routing. So routing still occurs between the areas. You've got the inter-area routing. So while many of the processor's intensive routing operations, such as recalculating the database, are kept within the area. Okay, so for instance, anytime a router receives new information about the topologic change, so within the area, including the addition, deletion, or modification of a link, so the router must rerun the SPF algorithm, creating a new SPF tree, and update the routing table. So the SPF algorithm is CPU intensive, and the time it takes for the calculation depends on the size of the area. Okay, so routers in other areas receive updates regarding topology changes, but these routers only update the routing table, not rerun the SPF algorithm. So too many routers in one area would make the LSDBs very large and increase the load to the CPU. So therefore, arranging the routers into areas effectively partitions a potentially large database into a smaller and more manageable databases. Okay, now that hierarchical topology that I'm referring to, okay, so share these advantages here. Okay, so smaller routing tables, reduced link state update overhead, and reduced frequency of the SPF calculations. Now in the multi-area OSPF, so the network are divided into different areas, but the requirement is all non-area 0, like area 1 here in the figure, and area 51 should be connected to the backbone, or area 0. So if you will observe here, area 1, which is the non-area 0, and area 51, which is also a non-area 0, it should be connected to an ASBR, okay, which are R1 and R2 of area 0. Alright, so let's talk about OSPF version 3. So OSPF version 3 is the OSPF version 2 equivalent for exchanging IPv6 prefixes. So recall that in IPv6, the network address is referred to as the prefix, and the subnet mask is called the prefix length. Okay, so similar to IPv4, okay, so this is its counterpart. OSPF version 3 exchanges routing information to populate the IPv6 routing table with remote prefixes. So take note that with the OSPF version 3 address families feature, the OSPF version 3 includes support for both IPv4 and IPv6. Okay, so OS address families is beyond the scope of this curriculum. Alright, so OSPF version 2 runs over the IPv4 network layer, communicating with other OSPF IPv4 peers and advertising only IPv4 routes. Now for OSPF version 3, okay, This has the same functionality as OSPF version 2, but uses IPv6 as the network layer transport, communicating with OSPF version 3 peers and advertising IPv6 routes. So OSPF version 3 also uses the SPF algorithm or Dijkstra's algorithm as the computation engine to determine the best path throughout the routing domain. OSPF version 3 has separate process from its IPv4 counterpart. So the process and operations are basically the same as in IPv4 routing protocol, but run independently. So OSPF version 2 and version 3 each have separate adjacency tables, OSPF topology tables, and IP routing tables. Okay? Now, the OSPF version 3 configuration and verification commands are similar to those used in OSPF version 2. Okay? So, comparing OSPF version 2 and OSPF version 3 data structures. Okay? So, basically, both version has the neighbor table, okay, topology table, and routing table. Okay, so it's just that OSPF version 2 is applicable only for IPv4 network, and OSPF version 3 is applicable for IPv6 network. Okay, so on this section, we will be talking about the OSPF packets. So there are types of OSPF packets. So the link state packets are those or are the tools used by OSPF to help determine the fastest available route for a packet. So OSPF uses the following link state packets or LSPs to establish and maintain neighbor adjacencies and exchange routing updates. So each packet serves a specific purpose in the OSPF routing process are as follows. Okay, so first you've got type 1. Okay, so the packet name is hello. You've got hello packet. This is used to establish and maintain adjacency with other OSPF routers. So it discovers neighbors and builds adjacencies between them. Okay, so the next one would be the type 2, okay, or also known as the database description or DBD packet. So this contains an abbreviated list of the LSDB of the sending router and is used by the receiving routers to check against the local LSDB. So the LSDB must be identical on all link state routers within an area to construct an accurate SPF3. Okay, so basically it checks for database synchronization between routers. Okay, so the third one is a type 3 or the link state request or LSR. So receiving routers can then request more information about any entry in the DBD by sending an LSR. Okay, so LSR basically requests a specific link state records from router to router. So the fourth one would be a type 4, okay, or the link state update. So this is used to reply to LSR or the link state requests and to announce new information. So LSUs, okay, or the link state update contains several different types of LSAs. So again, LSUs sends specifically requested link state records. Okay, so the last one of the OSPF packet is a type 5. Okay, so also known as the link state acknowledgement or LSAC. Okay, so the LSAC packet. So when an LSU or the link state update is received, the router sends an LSAC or acknowledgement to confirm receipt of the LSU. So the LSAC data is, or the LSAC data field is empty. Okay. Okay, so the next one is the link state updates. Okay, so routers initially exchange type 2 DBD packets, which is an abbreviated list of the LSDB of the sending router. So it is used by the receiving routers to check against the local LSDB. Okay, so a type 3 LSR packet is used by the receiving routers to request more information about an entry in the DBD. Okay, so a type 4 LSU, okay, so LSU packet is used to reply to an LSR packet. So a type 5, okay, or the LSAC packet is used to acknowledge the receipt of a type 4 LSU. So LSUs are used to forward OSPF routing updates such as link changes. Okay, so specifically, an LSU packet can contain 11 different types of OSPF version 2 LSAs, with some of the more common ones shown in the figure. Okay, so OSPF version 3 renamed several of these LSAs and also contains 2 additional LSAs. Okay, so these are the LSAs here. Okay, so with 6, 7, 8, and so on. All right, so note that the difference between the LSU and LSA's terms can sometimes be confusing because these terms are often used interchangeably. However, an LSU contains one or more LSAs. Just have to remember that. Okay, an LSU contains one or more LSAs. All right. Okay, so let's get into the detail about the hello packet. Okay, so the OSPF type 1 packet is the hello packet. Hello packets are used to do the following. Okay, so first, it allows discover OSPF neighbors and establish neighbor adjacencies. So advertise parameters on which 2 routers must agree to become neighbors. So elect designated router or DR and backup designated router or BDR on a multi-access networks like Ethernet. So take note that point-to-point links do not require DR or BDR. Okay. Now the figure here displays the fields contained in the OSPF type 1 hello packet. So we are talking about OSPF version 2. All right. So take note that we have here type 1, which pertains to hello packet. All right. So other fields are shown like router ID, area ID. So you're gonna understand more of it on the configuration on the next video lecture. Okay, so the next section talks about the OSPF operations. Okay, so now that you know about the OSPF link state packets, this topic explains how they work with OSPF enabled routers. So when an OSPF router is initially connected to a network, it attempts to first create adjacencies with neighbors, exchange routing information, calculate the best routes, and reach convergence. So the table here, okay, details the states of OSPF progresses through while attempting to reach the level of convergence or the state of convergence. Okay, so we have here starting with the down state, the initialization state, the two-way state, okay, the X-start state, exchange state, loading state, and the full state. Okay, so these are the OSPF operational states. Let's get into each of that state. So initially, the router is on down state. So on down state, no hello packets are received. Okay, so router sends hello packets and then transition to initialization state. So when you just configure, when you just connect 2 routers and you have not configured yet the OSPF, it is in down state. All right. So after the exchange of hello packets, okay, it will transition to initialization stage. So take note that in a down state, router sends hello packets. Okay. Now in the init state, hello packets are received from the neighbor router. So it contains the router ID of the sending router. Okay. And then it will transition to the next state, which is a two-way state. Now in the two-way state, communication between the two routers is bidirectional. On a multi-access links, the routers elect DR and BDR. So afterwards, transition to the next state, which is the X-start state. Now on the X-start state, on point-to-point networks, the two routers decide which router will initiate the DBD packet exchange and decide upon the initial DBD packet sequence number. Okay? So the next state would be the exchange state. So routers exchange DBD packets. So if additional router information is required, then transition to loading, otherwise transition to full state. Okay? So loading state, the LSR, okay, or the link state requests and the link state updates are used to gain additional route information. So routes are processed during the SPF algorithm transition to the full state. And the last one is full state. So full state is the link state database of the router in a fully synchronized form. So with a full state, the network now is in the level of convergence. Okay? So how about established neighbor adjacencies? So when OSPF is enabled on an interface, the router must determine if there is another OSPF neighbor on the link. So to accomplish this, the router sends a hello packet that contains its router ID out all OSPF enabled interfaces. Okay? Now the hello packet is sent to the reserved all OSPF routers IPv4 multicast address 224005. Okay? So that's a multicast address 224005. So only OSPF version 2 routers will process these packets. So the OSPF router ID is used by the OSPF process to uniquely identify each router in the OSPF area. Okay? So a router ID is a 32-bit number formatted like an IPv4 address and assigned to uniquely identify a router among the OSPF peers. Now, when a neighboring OSPF-enabled router receives a hello packet with a router ID that is not within its neighbor list, so the receiving router attempts to establish an adjacency with the initiating router. Okay? So first, it will be in down state to initialize state. Okay? So when OSPF version 2 is enabled, the enabled Giga Ethernet 00 interface, okay, in this diagram here, transitions from down state to initialize or init state. So R1 starts sending hello packets out all OSPF enabled interfaces to discover OSPF neighbors to develop adjacencies with. Okay, now during the process, R1 here, okay, so from down state, okay, so it will initialize or it will shift to the initialization state. And on that, so you've got the hello packet forwarded by R1 to R2. Okay, so something like, hello, my router ID is 172.16.5.1. Is there anyone else on this link? It will be forwarded on a multicast address 224005 where all the OSPF enabled routers are in there. Okay. Next would be the initialization or the init state. So R2 receives the hello packet from R1. and adds the R1 router ID to its neighbor list. Okay? R2 then sends a hello packet to R1. The packet contains the R2 router ID and the R1 router ID in its list of neighbors on the same interface. Okay? So afterwards, you've got now the two-way state. Now what happens during the two-way state? So take note that R1 receives the hello and adds the R2 router ID to its list of OSPF neighbors. So it also notices its own router ID in the list of neighbors of the hello packet. So when a router receives a hello packet with its router ID listed in the list of neighbors, the router transitions from the init state to the two-way state. Okay? So the action performed in the two-way state depends on the type of interconnection between the adjacent router. Okay, so it could be, for instance, if the two adjacent neighbors are interconnected using a point-to-point link or connected via a serial cable, then they immediately transition from the two-way state to the X-start state. Okay. Now, if the routers are interconnected over a common Ethernet network, then a designated router and BDR, or backup designated router, must be elected. Okay, so the two-way state would depend on the type of network you are working with. All right, it could be a point-to-point wherein routers are connected via serial link, or it could be a multi-access network, like a common Ethernet network, wherein there is a need for a designated router and backup designated router election. Okay, so afterwards, so elect the DR and BDR in case of the Ethernet network. Okay, so because R1 and R2 are interconnected over the Ethernet, so take note that these are G00 and G01, so this is an Ethernet network. So therefore, a DR and BDR election takes place. Now, as shown in the figure here, so R2 becomes the DR and R1 is the BDR. Okay, so take a look at this. So R1 has a default priority of 1 and the second highest router ID. So it will be the BDR on this link. So R2 has a default priority of 1. So both of them are using the default priority of 1 and has the highest router ID. So it will be the DR, or the designated router, on this link. Okay, so hello packets are continually exchanged to maintain routing information. All right, so how about synchronizing OSPF databases? Okay, so after the two-way state, so routers transition to database synchronization states. So while the hello packet was used to establish neighbor adjacencies, the other 4 types of OSPF packets are used during the process of exchanging and synchronizing the LSDBs. So this is a 3-step process, right? So decide first router, exchange DBDs, and send an LSR. All right. So decide the first router. So the router with the highest router ID sends its DBD first. Okay. So exchange DBDs. So as many as needed to convey the database. The other router must acknowledge the DBD with an LSAC packet. Send an LSR. So each router compares the DBD information with the local LSDB. So if the DBD has more current link information, the router transitions to the loading state. All right. All right. So let's get into the details. So decide first router. So in the start state, the two routers decide which router will send the DBD packets first. Okay? Now the router with the higher router ID will be the first router to send DBD packets during the exchange state. So in the figure here, R2 has the higher router ID and sends its DBD packets first. Okay? Next, exchange of DBDs. Now in the exchange state, the two routers exchange one or more DBD packets. So a DBD packet includes information about the LSA entry header that appears in the LSDB of the router. So the entries can be about a link or about a network. So each LSA's entry header includes information about the link state type. So the address of the advertising router, the cost of the link, and the sequence number, right? So the router uses the sequence number to determine the newness of the received link state information. Now in this figure here, R2 sends a DBD packet to R1. So when R1 receives the DBD, it performs the following actions. First, it has to acknowledge the receipt of the DBD using the LSAC or link state acknowledgement packet. Okay, so R1 then sends DBD packets to R2, and then R2 acknowledges R1. All right. Okay, so next would be sending an LSR. So R1, okay, compares the information received with the information it has in its own LSDB. So if the DBD packet has a more current link state entry, the router transitions to the loading state. Okay, so for example, in the figure, R1 sends an LSR, okay, so regarding the network 172.16.6.0 to R2. Okay, so R2 will respond, okay, on that LSR via the LSU. Okay, so R2 responds with the complete information about 172.16.6.0 in an LSU packet. Right? So again, when R1 receives an LSU, it sends an acknowledgement. That's why you have here LSAC or the link state acknowledgement. So R1 then adds the new link state entries into each LSDB. So after all LSRs have been satisfied for a given router, the adjacent routers are considered synchronized and it is in a full state. So updates, okay, so LSUs are sent only to neighbors in the following conditions. First, when a change is perceived, we call that incremental updates. All right, so it's in here. Let's go back to the slides. Incremental updates, and it is every 30 minutes. All right. Okay, so next would be the need for a DR. Okay, why is a DR BDR election necessary? Okay, now in a multi-access network, okay, so it can create two challenges for OSPF regarding the flooding of LSAs as follows. Okay, so first you've got the creation of multiple adjacencies here. So Ethernet networks could potentially interconnect many OSPF routers over a common link, like shown in the diagram here. Now, creating adjacencies with every router is unnecessary and undesirable. So it would lead to an excessive number of LSAs exchanged between the routers on the same network. Okay, so next would be an extensive flooding of LSAs. So the link state routers flood their LSAs anytime OSPF is initialized, or when there is a change in the topology. We call it topological changes. So this flooding can become excessive. Okay. Now, to understand the problem with multiple adjacencies, we must study the formula. Okay, so for any number of routers designated as n on a multi-access network, there are n, okay, and then n minus 1 divided by 2 adjacencies. So for example, the figure shows a simple topology of 5 routers, all of which are attached to the same multi-access Ethernet network or switch. Now, without some type of mechanism to reduce the number of adjacencies, collectively, these routers would form 10 adjacencies. How do we get that? So we've got 5 routers, all right? For n, 5 minus 1 is 4. 5 times 4 is 20. Divided by 2, that would yield to 10 adjacencies. Now, this may not seem like much, but as routers are added to the network, the number of adjacencies increases dramatically. For example, a multi-access network with 20 routers would create 190 adjacencies. Can you imagine that? Okay. All right, so flooding or LSA flooding with a designated router. Now, a dramatic increase in the number of routers also dramatically increases the number of LSAs exchanged between the routers. So this flooding of LSAs significantly impacts the operation of the OSPF. Okay, so an increase in the number of routers on a multi-access network or the network that is connected by a switch, imagine it will be flooded with a lot of LSAs. Okay, so if every router in the multi-access network has to flood, okay, and acknowledge all received LSAs to other routers at the same multi-access network, so the traffic or the network traffic would become quite chaotic. Now, on a multi-access networks, OSPF elects DR or designated router to be the collective and distribution point for LSAs sent or received. A BDR is also elected in case the DR fails. Now, all other routers become drawers. Take note that we only have one DR and one BDR in the segment. The rest are considered to be drawers. So a drawer is a router that is neither a DR nor a BDR. Okay, so take note that the DR is only used to disseminate LSAs. Okay, so the router will still use the best next hop router indicated in the routing table for the forwarding of all other packets. Okay, now to understand the problem of extensive flooding of LSAs, okay, so please refer to this animations here. Okay, now in the animation, okay, so R2 sends out an LSA. So let's wait for that. Okay, so R2 sends out an LSA. This event trigger every other router to also send out an LSA. All right, so not shown in the animation. Okay, so a required acknowledgement sent for every LSA received. So if every router in the multi-access network had to flood and acknowledge all received LSAs to all other routers on that same multi-access network, the network traffic become very chaotic. Okay. Now, the solution to managing the number of adjacencies and the flooding of LSAs on a multi-access network is the DR. Okay. In this case, we have R2 here elected as the DR and R3 here, which was elected a BDR. Okay. Now, on a multi-access networks, OSPF elects a DR to be the collection and distribution point for LSAs sent and received. Now, a BDR is also elected in case the DR fails. Now, all other routers become drawer. So a drawer is a router that is neither, again, a DR or a BDR. So R1, R5, and R4 here are designated as drawers. Now, the DR is only used again for dissemination of the LSAs. The router will still use the best next hop router indicated in the routing table for the following or for the forwarding of all other packets. Okay? So that would be the end of this video lecture. Thank you for watching and listening. Have a great day. See you on the next video lecture.